In this video, we're going to learn how to solve differential equations like this one. And I'm going to show you a kind of cool methodology called variation of parameters. Now, if you've never heard of differential equations before, well, check out the link in the description where I have an entire playlist that introduces the idea. But in this video, I'm going to borrow just a couple ideas from previous videos, and don't worry, I'll tell you about them as we go along. Now, the part that is particularly challenging about this differential equations is the right-hand side. This is called a non-homogeneous differential equation because of this tan of x. In contrast, an equation like y squared plus y is equal to 0 is a homogeneous differential equation. And the idea is that on the left-hand side, we have all the dependencies on y, and on the right, the question is it 0 or is it some other function? Now, the reason why this matters is that we have an entire theory of how to solve equations like this bottom one, this homogeneous case, and indeed its solution, I call it y sub h for homogeneous, is just a linear combination of sine and cosine. Don't believe me? Well, you can plug it in. Two derivatives of sine is just negative sine, and negative sine plus sine is equal to 0. Likewise for cos. And indeed, more than just stating the solution, we have an entire methodology to solve all of the constant coefficient homogeneous differential equations. It's a mouthful like this one that we studied previously in the playlist on differential equations. So our real goal here is how to modify this solution to deal with the tangent of x. And the approach that we're basically going to take is, let's look at that solution which we like, which worked well, but instead of having two constants, a constant times sine and a constant times cosine, let's make them be arbitrary functions. We know the functions can't be constants because if you plug those in, you get 0, and we want to get tangent. But maybe we can so-called vary the parameters, vary these constants in such a way that we get tangent of x. It's just a guess. I don't know whether it's going to work. I don't know whether it's going to work sometimes or always, but let's take that guess and play with it. What do I mean play with it? Well, what I really mean is let's take that guess and substitute it into the differential equation and see if we can find a u1 and a u2. First thing I do is just a bit of simplification. I'm going to remove the x's. So u1 and u2 are functions of x, but I'm just going to write it in shorthand just to make my life easier. But now that I have that, I can take my derivative. So first derivative, well, it's just two different product rules. When I look at this derivative, I notice that there are two terms in it that involve not the u1 and the u2, which is what I'm interested in, but their derivatives. I'm going to do a little bit of a funky trick here. I'm actually just going to set the sum of those two terms, the ones with derivatives, equal to 0. And you might think, hold on, Trevor, you can't just magically assume things are equal to 0. But I can. The reason is this. I'm taking a guess for my y, and I'm trying to see whether I can find a u1 and a u2 that can possibly substitute in and give you this value of tangent. That is, if I find such a u1 and u2, great. So if I add additional constraints, additional conditions that make my life easier, make it easier to find a u1 and a u2, as long as it solves the original problem of managing to be substituted in and equal to tangent, then it's okay that I've added these additional constraints. More heuristically, I have two functions I'm looking for, u1 and u2, so sort of 2 degrees of freedom, but there's only the one initial constraint, which when I plug it in, has to equal to tangent. And so I should sort of expect heuristically that if I add one more constraint, and I have 2 degrees of freedom and 2 constraints, that hopefully that is something we can still solve. Well, let's see if that's true. So with this condition that they're equal to 0, I'm going to get rid of these two terms. Things are a little nicer. And then when I take its derivative, well, again, we get two different product rules showing up, and we get this sort of gnarly second derivative. Now what I want to do is take all of this and plug it into the original equation. So I'll take that y double prime, I'll plug it into the original equation. I'll take the y, I'll plug it into the original equation. But because I'm adding these, I notice there's a lot of similar terms. Like I have a positive u1 sine of x in y, and then I have the negative of that term in y double prime. Likewise, positive u2 cosine of x, but negative of that term in y double prime. So there's a lot of cancellations, only two terms that remain on the left-hand side, and so I just have u1 prime times cosine minus u2 prime times sine, all of this equal to tangent. This is one condition. The other condition is that one that I sort of arbitrarily impose, that they have to add up to equal to 0. And now when I look at this, I have a system of two equations in two unknowns, u1 prime and u2 prime. So there's some hope here that I can solve this. And indeed, I can, because if I notice these two terms, there's a minus and a plus. They both have a u2 prime. And so what I'm going to do is I'm going to take the top equation, multiply it by cosine. The bottom equation, I'm going to multiply it by sine. So now those two terms are identical. So when I add them, because of the difference in sign, they go away. And all I'm left with is u1 prime times cos squared plus u1 prime times sine squared is equal to, well, the right-hand side, tangent times cos. That simplifies just to be sine of x. By the way, I'm going to make a domain restriction that I'm only looking for x values between 0 and pi to sort of get rid of some of these domain problems that could occur. Regardless, I look here, I've got cos squared plus sine squared. That can be combined to 1. And now I have u prime, u1 prime at least, equal to sine. If I want to get to u2 prime, I just plug sine of in, and you can quickly get that u2 prime is tangent times sine. A bunch of substitution in, a bunch of solving for this system algebraically, and I've got this result. So where are we in our larger development? I began with this differential equation. I made this variation of parameters guess where I'm trying to find a u1 and a u2, and I've almost got that. I've got their derivatives. So to get to the original u1 and the original u2 like I was setting, let me just take an integral on both sides. The integral of sine is easy, it's just negative cosine plus a constant. And then the integral of tangent times sine of x, that one actually is a little bit obnoxious. It's related to the same way that the integral of secant is obnoxious. So it's a bit of algebraic trickery. I'll let you try and figure it out down in the comments if you're so inclined. But the solution to this is, well, 1/2 logarithm of the absolute value of sine x minus 1 over sine x plus 1 plus sine of x plus a constant. The constants are a little bit like the ghost of the homogeneous solution. If you just have the terms that come from the constants, those are going to add up to 0. The other stuff is the portion that's going to add up to tangent. Nevertheless, we were searching to see, could we find a u1 and a u2? And yes, we can. We found a u1 and u2. This solves our original differential equation. Okay, so how does this apply a bit more broadly? The category of differential equations this works for are ones that look like this. These are linear differential equations. So that is, I have y and its derivatives linearly with coefficient functions, and those coefficient functions only depend on the independent variable x. I have a non-homogeneity on the right-hand side. And the methodology is exactly what we've done before. So the theory from the homogeneous portion, if you imagine g of x was 0, is that I can always get these two linearly independent solutions, y1 and y2, on some nice conditions on the p of x and the q of x at least. Then I can go and try and make the same guess, where I will vary the parameters. I will guess a solution that is a u1 y1 and a u2 y2. Plug that all in, and you can do the same basic work that we did in the previous example. Leave it generic. Don't put sine and cosine in. Leave a generic y1 and y2. If you run through the algebra exactly as we did, it's a great exercise. I encourage you to do it. You get these formulas for the u1 and the u2. So we've solved the solution. Now, we have to be a little bit careful here. So 2 points to observe. The first thing is, in both of these integrals, I have a denominator, which maybe could be 0. But if I look at the two denominators that I have, notice they only depend on the y1 and the y2. Well, we get to use a little bit of theory to save us. Because this expression here, also known by the way as the Wronskian, if you've seen that before, these expressions in the denominator are never 0 because of our initial assumption that the y1 and the y2 are linearly independent. We've seen previously some theory why that is the case. So we have these integrals, and the second point then is, can we actually evaluate them analytically? Well, it depends. It depends on the integral. And indeed, the whole point of solving a differential equation analytically is that we don't want to have to rely on a numerical method. Because I mean, we could numerically solve these integrals, but likewise, we could have numerically solved the original differential equation. If we're looking for an analytic solution, it ultimately comes down to our ability to solve integrals. And this is very common in differential equations, where ultimately your ability to solve a differential equation rests on converting the answer into doing some integrals, which you may or may not be able to do. Regardless, if you can find the y1 and the y2 initially, which is not always guaranteed, and if you can do the resulting integrals, then the variation of parameters method always works. I do want to contrast this with the other method that students often see to solve a differential equation like this one, a method called undetermined coefficients. Undetermined coefficients works by guessing a solution that looks like tangent of x. For example, if it was sine of x, you might have guessed a solution that was like a combination of sine and cosine, and that guess turns out to be often very useful. But that method doesn't really work here, and it's because the derivatives of tangent just keep on getting messier. Like, first is tan, then it's secant squared, then it's 2 secant squared times tan of x, and so forth. The more derivatives you take, the messier and messier tangent of x gets. It never gets to be written as a linear combination of the previous derivatives. So there's no real hope of guessing something of the form tangent of x and having it nicely cancel out. Undetermined coefficients, which I have a whole video on, that is great. It's a nice algebraic method. You don't have to do integrals, but only sometimes works, whereas variation of parameters, up to our ability to do integrals, will always work. So depending on what your context is, you might prefer one or the other.